Today. I'd like to welcome Benjamin Prautsch today to our analog work group meeting. I'm helping Mehdi, by the way, help host this today as Mehdi is traveling. So appreciate that. But look forward to your chat, Benjamin. And then after that, Hungji will be providing an update on his work after that. So Benjamin, go ahead.
Thanks a lot, Robert. I just see I made a copy-paste mistake here because basically the presentation I held here is kind of a mixture of a presentation I held exactly there at AustroChip conference end of last year, combined with the webinar I held in March this year. And I hope to give you an overview of our activities and hopefully also identify, for example, cooperation potential, because cooperation is also what we are always looking for. And especially, well, as you know, analog is very special, as of course also the automation of it is, and therefore I think it's always interesting to discuss and align. Wait, I said sorry. I just selected the wrong slide deck. I'm back. Your screen. Yes, I'm sharing soon again. Here we go. Now it's the right. Now it's the right slide deck. Okay, please excuse this. All right, so now I'm on track. So please excuse this. First of all, I would like also to stress that the work that I present is largely supported and funded by the German Federal Ministry of Education and Research. So we do a lot of research activities. We also do industry activities, but that's the acknowledgement to the funding we have been receiving for a while, and that we have, and that's still going on. And I would like to start with a brief introduction of Fraunhofer itself, because it's maybe not exactly clear who or what Fraunhofer is. So Fraunhofer Gesellschaft is, or Fraunhofer, is an application-oriented research facility. It tries to bridge the gap between university research and industry. And we have roughly 30K employees at Fraunhofer, all across Germany. So everywhere in Germany there is an institute, and we have 76 institutes all across Germany, with a budget 2 years back, 2021, with 2.5 billion. And the funding structure is such that 1/3 roughly is, or say 70% is either basic funding or funding or research projects, and 30% is what we also work together with companies in order to really implement this bridging the gap between university and industry. And we belong to the Fraunhofer Institute for Integrated Circuits, IIS. That's the largest of all the Fraunhofer institutes. It's located in Bavaria in Germany, 1,000 parts. And we here specifically are located in Dresden. So the heart, I like to say, the heart of Silicon Saxony. That's where we are located. And this division engineering of adaptive systems, here I also have some figures. So for example, just to highlight a few, we have quite a bit of laboratory where we provide, for example, measurement also for customers. And recently we made a tape out down to 5 nanometer, and we have several tape outs. We work on the design side, but also like system modeling aspects of this. And as a final slide of this advertising part, again, as Fraunhofer, we do both funding projects, but also contract research. So this means on one hand side, we might appear as a university, but in fact, we appear rather like a company. So this means individual contract research can always be aligned with us based on individual agreements. This might be education-wise, might be consulting or workshops, pilot feasibility studies, individual project ideas, or the licensing of IP. Might it be hard IP or soft IP? Okay, and in this frame, what we are working on in our business area efficient electronics is as one aspect, of course, the design of microelectronic circuits. So the design part and the of course the manufacturing is done by a third party, but then we test this in the lab. We are also pretty active in the advanced packaging field. And of course, the topic of today, we work on analog design automation. And that's exactly what the focus of this presentation here is. And well, as you in the analog working group, of course, know well, we have pretty much a gap between analog and digital. So here to put this in some figures, while on the digital side, we do have synthesis. On the analog side, we still largely have manual design. Of course, there are, especially recently, a lot of attempts to increase automation on the manual analog side. But the major challenge still is that what maybe takes a few tenths of minutes in digital might require as much as weeks or even months in analog. And that's definitely a problem to, well, SoC designs. And if we dig a little bit deeper, the challenges that we see, or on the design side, some major challenges we see is that due to the low level of analog automation, both miniaturization and nanoscale effects, as well as the increasing system complexity, of course, get more and more a challenge to the design problem. And what we propose as solution here is to consider both two aspects. One is to systemize the design flow, and second is to automate the design flow. Our approach here is, and I will detail this later on, is very much generator based. So automating building blocks, integrate the methods into the flow. And here we follow a technology agnostic approach that I will detail. And maybe you have seen the presentation. This is also available on YouTube from Christoph Sandner from Infineon. So because he made a slide that I really liked, therefore I adapted this. So that's from his presentation that I referred down there. In the typical manual design, of course, you have the design phases and several versions of IP, and it's relatively constant the time you need to even reuse IP. And the generator-based approach is the idea that you invest some initial time for the underlying EDA in order to then build like the first generator and maybe a second or derive a second generator and so on. And that across a family of products, you will see some savings. The big question here, of course, is the question how much to be invested in the EDA in the first place. And this is where I like to talk about the sweet spot, because I think that's really a topic where design experts and EDA experts have to align to identify really those parts that can be automated pretty well. And in order to dig a little bit deeper into this reasoning, we tried to sketch briefly, roughly the individual design steps that we see in IC design, of course, starting with the requirements and then based on modeling, it runs all the way towards sign off and then finally manufacturing. Later on, of course, also measurement. But here the focus is the design part. And today, this is pretty much done manually. Of course, the many tools improve over time, level of automation increases, but essentially it's a manual task. Design experts are sitting on computers and do stuff in a manual fashion. And the general idea, of course, now is to add automation tools on top of these individual these individual tasks in order to even, based on this automation, even improve the level of reuse. Because if you have automated an individual step, you can preserve this for later on and then rerun this automation step. And that's basically automation for an individual design step, but putting the pieces together in a consistent flow is then even the next step where we believe, that's the way to go in the mid and long run. But today the focus will be especially on the circuit design side, and on the layout design side, a little bit on the floor planning, but also on the layout generator. So aspects around this is also tasks that project partners are working on, or where other teams in our institutes are working on. But this here should be the focus for today. And I would also like to bring in a site. It is just a secondary source, but I like the site pretty much, that analog circuit design is like chess. Just because you know the pieces, just because you know how the pieces move doesn't mean you know how to play the game. And I think there are some interesting thoughts inside. One, of course, is to even know the pieces, and then also to know how to put the individual pieces together and then do something with it. And I would like to trying to say scratch the surface about some of the pieces and maybe some ideas how they could play together. And one part of the thought process that we had was that, of course, on the manual, that we have maybe roughly two axes. One is, say, the level of automation. The other axis is the hierarchy level, like how complex the block is that is automated. That's definitely not a complete map, but it tries to sort this a little bit, while we can also see that, of course, the big players, they all work on design acceleration. They bring in new tools and add-ons to improve the manual design method. But quite a bit differently works the procedural automation, where really parts of the design are automated. Very much known, of course, are the P-cells, very low on the device level. But based on those pre-cells, the idea was adapted. Best known, from my point of view at least, is probably the Berkeley analog generator. Meanwhile, even in the third version available and even open source. So the Mosaic group, for example, is building upon the findings there. The approach that I present today, so our intelligent IP generators, are also a procedural automation approach, but even in the market, there are several optimization methods. Some on the layout level, like Parsec Animate, others on the sizing level. And to dig a little bit deeper into the underlying methods, this is now, by the way, exactly the figure that Mehdi was asking, as far as I understood him. So the underlying methods are threefold, or could be categorized like this, but this is not my idea. That's from Ricardo Martins et al., as given on the at the bottom. So we have procedural approaches, we have template-based approaches, and we have optimization-based approaches. I will detail this in a second. And of course, time was going on. That's, again, not a complete list, but it tries to highlight a few of the approaches, as, for example, the Berkeley analog generator on the procedural side. But there recently, of course, there are also tools like Align and Magical. In between the green marked publications, that's our those are our contributions, where one can also see that we started as a procedural and we try to go more towards template-based and optimization-based. And I think when it comes, of course, to open source, what I find quite interesting is that especially Align and Magical, they had multiple versions. So they started in 2019, so that's the latest sources I know. But then came up with updates, and the open source aspect here, of course, is quite driving, and that's something we are also looking at very much. Okay, but now a little bit deeper dive into the methods. So I mentioned there's the optimization-based approach. So there was this nice drawing from Rutenbar already proposed a while back, where an optimizer basically has an optimization engine and an evaluation engine where candidates are generated, and among the candidates, it will be selected which one is right or which one is on the right direction. One thing we need here, of course, is constraints, where even whole research fields are active to discuss the topic of constraints. And if we put both together, then we will yield, like here in this publication from Lorenzo et al., some nice plots with trade-offs, even in this case, even considering layout effects to really see how trade-offs are when even layout is considered. And a special form of a constraint is the so-called template, which basically might be understood as a floor plan. It's like a slicing tree, like this one. Also, here, this is from a paper from Castro Lopez et al. Back in 28. And the underlying idea is that based on the template, which is just a relative placement, the actual implementation can be found. Like as you can see here, for example, block M and F, they are always located roughly at the same place. Because the relation is stored, but the actual implementation of shape and size, this is part of the optimization process. And then, of course, like filling the gaps by proper alignments or sizing, or even building block parameterization is crucial here. And the actual geometry that is generated underneath the templates, that's where we get to the procedural generators. And that's essentially a programmed procedure that takes parameters and outputs, for example, layout or any other sort of data. And the underlying idea here is that, not in an iterative way, it is analyzed what the solution could be, but it's rather a known strategy that is coded into the procedure. There might be, of course, some conditional statements. There can be a lot programmed inside, but the basic idea is that something known will be used and is essentially rerun. And this is already used, of course, in analog design today, because probably almost all the basic building blocks, like here, transistor building blocks, are automated as of now. It didn't, that was not the case in former times, but today, at least in my experience, there are not so many that customize even those building blocks. And if they do, they would likely build a P-cell out of it. If, for example, they would like to have a very special transistor shape. But there we already see the automation. And now, of course, there came the question, like, how to benefit further from such generators. And the straightforward idea, of course, is, increase the level of hierarchy to benefit further from the generators. And this is also what we did, or colleagues of mine did back in 2013, Thorsten Reich and colleagues. And it is possible, you can program it, but there's, of course, there's the challenge to identify, where can I really benefit from the reuse? And that's exactly where this initial invest of EDA comes in. And what we learned over time is that, of course, we can build complex generators, we can build base level generators, but the focus then shifted pretty much more to the smaller building blocks, because with this typical generator or procedural generator-based approach, programming such large structures turns out to be tricky in terms of reuse. And therefore the focus was more on the basic building blocks. And again, to detail a bit how our approach here is, I again have a simplified design flow from specification over topology selection, circuit design, layout design, and then layout verification, where the underlying idea is that during the design, after initial efforts, we can sometimes select a previous topology and definitely use building blocks along the design flow in order to yield a faster design and or reduce the design risk. Of course, the acceleration on the bottom end depends on the initialization on the upper end. And that's exactly where I already mentioned this term of the sweet spot, where really EDA people and design or EDA experts and design experts should well align where the sweet spot really is. And a little bit more on our, specifically on our methodology. So we call our tool Intelligent IP, or short IIP. What we focus on is to make it user-driven, so that designers have control, like in the P-cell, and that they can, define and parameterize various aspects of the generation result, while the generator method itself is pretty PDK agnostic. So we have been using IIP in 350 down to 22 nanometer, now made some first proof of concepts internally, to see how the method runs. And we always use the P-cells from the PDK as part of the generated structures that our generators build. And another differentiation to P-cells is that the full design data is really generated. So right in the design library, data will be generated in a persistent fashion, but of course by the design method or by the IIP method, it is parameterized. And I already mentioned this challenge about low complexity but high reuse, and high complexity and low reuse. And this led us to basically three main applications for the generator method. So we already built an IIP, our framework that we call the IIP framework, where all the flow integration, etc., is implemented. Also the handling of technologies. So this is what we also offer to customers. And then on top, we have basically three modes of how we believe generators can be applied. So one is kind of the out-of-the-box generator. That's like kind of a default generator for default building blocks. Second is a pillar of reuse, where when porting from one technology to another, or from one specification to another, the generators can accelerate. And the third is really that based on custom needs, a custom generator is built. This might be by our method, this might be by, for example, skill programming. But this is basically, the categories that we identified is probably worth thinking of. Okay, and I would now like to go a little bit, through those pillars to give you an idea of our method and also of our underlying thinking of the approach. So here is basically the first pillar, where on the right-hand side you can see a schematic. There are building blocks which are already generated. So as illustrated here, the generator user interface is in the middle, and using this you can build up the schematic in this block level fashion. As the whole design data is generated to all those blocks, there is already a layout corresponding. You can of course customize the layout, for example, number of rows of unit devices and many other aspects like routing width, for example. But this layout view is already in place, and the generator allows to define the specifics. So this is mainly, of course, the device sizing, but also those layout parameters. And while this can be used in a GUI mode, this can also be used in a scripting mode. And with this approach, a flow can be automated. For example, running by using a parameter file or by sending just the command with parameters to the cadence CRV, for example. Okay, but to give you even more an impression how the generator works, I have a screencast here for you. So in this case, now a unit device sizing is adapted. The generator is run in the background, and then the generator building block, in this case here, the topology was already predefined. One can basically build up the schematic. And if you now start at the schematic and run the schematic driven layout, then we can basically go through the typical routine. And on the right-hand side, you see how the generated building blocks correspond to the schematic level building blocks. So, and this is exactly what I just mentioned before, automation on the building block level, as here, for example, for differential pairs, because there's a special generator for differential pairs, but there's a more generic generator for very arbitrary structures. And this is basically the mode on schematic level design entry and then usage on the layout level to accelerate the design. And this was, for example, used here in a project in 22 that was a SAR ADC. So here, for example, roughly 60% speed up could be reached. So you see, not all the blocks were automated, but the designer decided for some blocks to be automated. And and on the right-hand side, the fields that are marked, they are also automated in part. So that's basically a combination that is always possible that designers can decide what parts they automate and what they still do manual. Or another example here in the 130 nanometer PDK, on the left-hand side, you see the plain devices, so just the P cells. On the right-hand side, there is a scenario where the devices were already encapsulated in building blocks like current mirrors, differential pairs. And in both cases, the place and route or the placement, the autoplace from the design environment was used. And here you could, well, in this case, the amount of complexity could be reduced into the building blocks. Okay, back to the three pillars. Of course, you are not always happy with some generic solutions. So what we also identified is that depending on the problem, of course, we will need some custom generators. And the typical flow with custom generators is always that there will be a phase where the generator is specified. And that's exactly, again, what I mean with this sweet spot. Design experts and EDA experts really have to understand each other to find those parts of the design that are reasonable, well, where it's reasonable to automate. Then there happens the actual generator implementation in order to then apply it for design. We applied this specific methods is given here. Quite a while back, we implemented a flash ADC, for example, just to see how far we could get in terms of the complexity, and also to, how much we can reuse from a former design. So there was basically a design already done, and this manual design was then implemented as a generator. So there was like roughly half a 4 months or so of implementation to have the generator at hand, which then was running in both, or executing in both 180 and 350 nanometer, and was also flexible in the resolution in this case. Another example that was for an interface generation where we wanted to make sure that the right net is located on the right spots in the layout. Of course, this can be, well, could be done manually, but here we had a very specific pattern in mind, and yeah, decided to make a generator that is basically file driven, so that in the file it specified how the position and how the nets are related, and then the generator just executed, and we could reduce yeah, the risk here. Or another example, here we simply identified, well, we need some scripting because the designers, they were doing similar shape drawing over and over again. So here the simple answer was we built a small user interface and skill scripting in order to automate exactly those repetitive tasks. And this is exactly the underlying idea of a procedural generator, but just applied here by means of yeah, some skill commands. And one final example where we also identified that this is or can be a good sweet spot is the automation of test structures. Here we extended the generator also by a small GUI that yeah, reflected some routing schemes. And this was again also file driven. So the file was loaded by the generator. The mask is still there, could be changed, but doesn't have to be changed because the input file in this case was basically an Excel sheet. And based on the Excel sheet, then different yeah, test structures were generated. And later on, we also adapted this generator for some RF test structures. Okay, so I guess that was yeah, those two pillars. A big question, or what's maybe of interest for you is also the question if building your own generator or even your own IIP generator is possible. And here I would like to give you a brief idea how the generator is programmed in general, because or give you a tiny little idea about how our API is constructed, because all our generators have all the same structure. So they the generator class reflects the user interface or this GUI, the schematic level generation, the symbol generation, as well as the layout generation. And on the GUI side, we have a procedure that basically defines the parameters. Then we have a procedure that defines any callbacks. Then there comes one procedure that prepares data in order to make sure that data is similar across the target views. And then we basically have the individual views as the schematic or the layout symbol is not highlighted in this case. And in order to even reduce the efforts here, we have a tool that we call the IIP Creator, which is a tool that takes an existing schematic and makes fields basically this structure with all the information, like all the P cells, all the wires, all the pins, all the sub generators into this generator structure in order to help generator developers to build their own generator. And this now basically brings us to this middle pillar that I also mentioned before, this path of reusing designs. And here the idea basically is we start with a design, have a tool to make code out of this design. So the layout part is not yet covered, but that's under construction. And then use this generated code to run the generator either, for example, across flavors or across PDKs in order to have enable reuse. And the more we use generators in the source design, the more we can benefit in the target design. And here, in order to also illustrate how this appears to the user, we can select the generated generator. So what you can see here is fully automated. So there was no programming involved to reach the state. We see on the left-hand side various parts in the tree, and here with a list of sub-generators that are all generated by this main generator. And if now the apply button is hit, in this case, roughly a minute, you see the design, the library fills up with building blocks, and those building blocks cover schematic, symbol, and layouts. And as you can see here, it's always all those three views, and therefore they are reflected on the design side. So we have basically the source schematic typically doesn't change pretty much, but of course a lot of the details will change in the on the layout side, and that's basically the approach of the IRP creator. But as you can see, the layout is basically just placed side by side, and that's a more recent activity that we did. This is where we really embedded those templates that I mentioned in the beginning, that we implement them into the generator. Here, a simple example. On the left-hand side, you have the user interface. In the middle, you have a representation of the template. But there are no dimensions, so a template does only know relative locations. And on the right-hand side, you have an implementation where design data is generated. Here, for example, number 4, number 3 corresponds to the respective location on the right-hand side, while the size always depends on those building blocks that are generated. And if now this approach is used in a hierarchical way, we can build up even more complex structures. So for details, you can see on the lower, on the bottom, a recent paper that we made. So where the key idea is that we enable users to control selection and some details of those templates, so that they have control over the generation process. And in this way, they can change parameters and generate a variant like we see here on the right hand side in a matter of roughly 2 minutes, and if the user is not happy with the result, the user can go back to the user interface, exchange blocks, for example, or change metal layers, metal width, and the like, and generate a new example and feed this then back into the flow. And this now brings me back to this figure that I showed in the beginning. So I showed these individual steps. I showed what runs manual today. I showed what we propose to set up to automate. And this way designers can build circuitry. They can automate their own generator, build or generate initial layouts, then of course make, for example, the post layout simulations, and relatively quickly run this iterative loop. Okay, but the big question, of course, remains what exactly this sweet spot that I already talked about would be. And I think there's not really a general answer, but just to give the idea. So while there are tasks where generators really can help, there are tasks where design experts should take and have the control. And I think it's always important to align really what should be automated and what should be done by the designer. And for this reason, we always propose whenever such a problem appears, EDA experts, design experts should make a workshop. This is also what we offer. But in general, they should really sit together and then maybe iterate, make some first tests, try out ideas, and only then get in the actual integration phase. Well, and finally, some conclusion here. Analog IC design, as you of course know, is complex and challenging. The communication between design experts and EDA experts, I believe is really the key to enable and improve analog automation. And there's probably not a one-size-fits-all solution. So there should always be an alignment of combining methods that automate reasonable parts of the design. And this is, of course, all based on really good alignments among the domains EDA and design. Based on a good understanding that either of them really understand what the other is talking about is probably the key to yield this sweet spot. And that's basically the underlying idea that I wanted to bring, because the question was, well, there are chances, there are hurdles. Communication is probably one of those hurdles, but there's also a good chance to really accelerate analog to get rid of maybe not so nice tasks and even improve the design performance in this mixture of EDA and design. And with this, thanks for your attention. Here's also my contact for your information.
Thanks, Benjamin. That was a great presentation, very informative. I truly enjoyed it. Are there questions from folks in the audience?
So by the way, here's a list of related publications that we made. So
I did have one question. I actually, your commentary there at the end relative to EDA developers working hand in hand or in close partnership with design folks really has been the underpinning or hallmark of my career, which is now at about 40 years in full transparency. But one of the things that I've been advocating for along amongst others in industry for quite some time is really what I would call is an EDA toolkit approach, which is effectively that the major EDA suppliers, which have of course, a very stable design platform, make their tools more like a toolkit and something beyond just a Tcl or Python API, right? So like the work you're talking about, you really need low-level, source-level access to be able to do the things that are required by the design community, specifically analog in this case. And my experience also has been is that the EDA companies are a bit farther removed from actual design, compared to what's really needed. So I just wonder if you might comment a little bit about where you see the current landscape on this topic is.
Yeah, I think that's maybe the challenging part, because the business model of the big players doesn't necessarily support an open approach. But the open approach is what we need in order to put the pieces together. So if you just consider individual steps along the design flow in say more or less closed design environments, where you can't really get full access, as you just put, if there is maybe some skill or some Tcl scripting, and if you want to link Python into it, then you need to build your bridge, and this is always not really included. I think that's something that we can't really solve technically, but this is rather a business model decision of the big players. So I don't know the exact details, but recently it was announced that maybe Cadence will open the environment a little bit more to at least plug in other optimizers for the simulation. But I don't exactly know the details. But I think, well, maybe the open source trend is pushing this a little bit, but I also see the different interests, and I don't really have a really good answer other than stating that's a kind of interest conflict. And the big players, well, if they open more, this will definitely help to automate more, from my point of view.
I appreciate it. Are there questions? We have time probably for another question or two from anyone in the audience.
Yeah, apologies if I missed a very basic thing early on. Is this what is this? Is it a piece of research or a product you guys are selling, or available, on GitHub somewhere?
It's the topic of openness, right? It's both research and the services we provide. So everybody who is interested in having such a generator evaluating it or using it in design, either as like ready generator or as the tool itself that you could implement generators. That's exactly where we are located here on both sides of the spectrum. So we do have funding projects where we developed large parts of the software, and in specific contract research, we can apply the method for a dedicated problem based on customer specification.
I do have a question, Benjamin.
Yeah.
So what are the design you targeted? Do you have a portfolio, right? So automation, I mean, it sounds like you're able to do some automation there. But then what are the building blocks for portfolio of IPs you're able to generate here? And how do you, how do you compare? Because you mentioned at some point Magical and Alliance. So how did you compare to these tools? Have you been able to run them?
We have not yet run them on our own. So we discussed with the users, and we also try to understand the approach there. Of course, Align and Magical, they are much more on the automated side of the spectrum. The Berkeley analog generator is also very much on this programming side of the spectrum. So I think the key comparison is that we combine the automation with a service on top. So we can use our methods for your specific design problem, design challenge regarding available IP. As our colleagues that are into design also use our method, we have several especially ADCs that's where this method is inside.
But since you're doing a template-based approach, right? You're supposed to have some design already predefined, right? Which you basically resize or and so on. Are you able to hear me?
Yeah.
We hear you.
Yes. Essentially, this method here is mainly really the EDA side of the spectrum. So I did just show a few examples like ADC. We also had other ADCs really programmed in the past, but that's what we identified over time, that it's better to really build the design, or that might even include the whole generator as EDA, as an offer that we build together with the customers specifically. So we do not really have this catalog of generators that we could offer, because in the past I guess it's pretty similar to the IP business. There are also many IPs available, but then there are some updates and changes needed. And what we face is that this also reflects the topology, and this means it's probably best to build such a generator together with the customer right away, or provide the method.
So when you build the generator, are you building it for a large design space, or are you building it just for one specific target specification? Right. So if it is a generator.
Well, I guess the template approach, the idea of the template approach that we just included recently is to widen the spectrum of performances. But of course, in the end, if you have one topology, you are pretty much in one spot of the possible design space. So you might use hierarchical attempts to like combine different types of IP or even parts of IP to reach a broader spectrum. But we recognize that it's rather important to be in kind of a region and more optimized for a region, and then maybe consider a family of products to consider the next scaling step, for example, or things like this, rather than trying to capture the entire possible solution space, because the latter is probably a little bit too far.
Okay, thank you.
So thank you again, Benjamin, for your presentation. So we have one more talk we want to do today, but
Thanks
folks,
for
feel
having me.
free to follow up with Benjamin. No, thank you. It was very informative. I really did enjoy it, and share your
Appreciate
slides
it.
as well when you have a chance. So thank you.
You're welcome. Right. In case of any questions, here's just my contacts again.
Thank you. Hung-Chi, did you have some talk you wanted to share today?
Yeah, actually, we would like to update something from our side. Did you hear me now?
Yes, we hear you.
Okay, great. Sorry. So because Christian is going to present have a presentation in a few minutes, so please allow me to give you some updates from our side. So I don't have the presentation today, but I will just, if it's possible, I'll just go through it like this. We have done the room temperature measurement of SkyWater 130 technology using the probe card. But the thing is that we have to probe it manually. We don't have the automatic probe station, so we have to move the probe card one row by another row. So after gathering some room temperature DC data of the SkyWater 130, we also did the data extraction. But this part is automatically do the data extraction for the simplified equipment model. And those of the results are already available on the GitHub. And our next point is that we would like to do the cryogenic measurements on the IP, the cryogenic IP measurement on some text structure. And we are also happy to do the measurement if available on the 180 GF block technology. And right now we are looking for students to design some basic analog blocks using the design-oriented model, which is a simplified cable model, and apply the design methodology to eventually tape out it and validate the whole concept. So this is our plan right now. And so may I have asked a question? Is it possible to get some test structure on the 118 nanometer technology?
Could you repeat that last bit, Hung-Chi? Unfortunately, your audio is a bit distorted here today.
Oh, sorry.
So
I don't have the good.
Just to give some background. Yeah, so just to give some background here, Rob, we discussed yesterday with Christian and Hung-Chi, and trying to figure out is there a way to do another technology for any other nodes? And there's interest in trying to automate some of the structures and test them for higher temperatures. So we already did that with NEST in MPW5 and 6 and 7. So this is some background to what Hung-Chi is mentioning here.
Okay, thank you. What is there a particular other technology node that you're considering, or what's of interest?
Like 180 GF block.
Ah, right. Okay.
Yeah, we are considering to do. I mean, we also are happy to do the measurement of 180. Yeah, and because now we are thinking about whether we are go further on 130 or 180 to validate the model parts and the
Makes sense.
Yeah, so the other thing, Rob, is we're trying to build up a suite of small test cases, and this test structure seems very relevant to analog automation because we can test all the available EDA tools, right? Like Align, for instance, or maybe Bag if it's open, and what Benjamin is discussing. So, and the OpenFA soft, obviously, and see, we can develop these approaches and have some type of standard here in CHIPS Alliance with all these tools. So So that's how so that's what we discussed yesterday, and maybe we can develop that over the next meeting leadership line in this kind of working group.
That makes a lot of sense. I think that would be great.
Awesome.
Any questions or comments from folks? All right, Mehdi, anything else from your side?
Not really. Thanks for helping. And thanks everyone.
No problem.
Yeah.
All right, thank you everyone for attending today. I really appreciated the both updates. So thank you so much.
Thank you so much again.
Thank you.
Yeah, thank you, Benjamin. Very good. Bye-bye.
Bye-bye.